Let G be a group of order 7 and phi x defined as x raised to the power 4 and x is coming from group, then phi is not 1 1, not on 2, not a homomorphism, and option D is 1 1 on 2 and homomorphism. In this question, we have to test three things: 1 1 on 2 and homomorphism. You can check all four options, and these all four options about 1 1 on 2 and homomorphism. Given condition is G is a group and order of G is 7 and 7 is a prime number, and we know that a group of prime order is always cyclic. This is a theorem, cyclic, and every cyclic group is abelian. Indirectly, property of commutative group is given. We need to check 1 1 on 2 and homomorphism. First, what is the information given? As G is cyclic and order of G is 7. Because G is cyclic, it is generated by, suppose, X. So order of G will equal to order of its generator, and generator gives x raised to the power 7 equal to E. This is the property of generator. And this is least positive integral power when we get E. As phi is given, phi x, the rule for phi is given x raised to the power 4 for all x is coming from G. And suppose here this x is group element and this is generator, so you can change generator as a, avoid confusion. So phi a will be a raised to the power 4 as expression of phi is given. Phi of a square, as this is input, and how phi gives output. Input raised to the power 4. Input is a square. So a square raised to the power 4 gives a raised to the power 8, and it can be written as a raised to the power 7 into a, and this is nothing but e. So this is a. Means a square is a. Now phi a cube will be a cube raised to the power 4, means a raised to the power 12, means a raised to the power 7 into a raised to the power 5, and this is e, so a raised to the power 5. Phi a raised to the power 4 will be a raised to the power 4 raised to the power 4. By defining nature of phi, it will be a raised to the power 16, and it can be written as a raised to the power 7 into 2, so a square. Phi of a raised to the power 5 can be written as a raised to the power 5 raised to the power 4, and this is a raised to the power 20, and it can be written as a raised to the power 7, 7 and 6. So a raised to the power 6. And last one is phi of a raised to the power 6 will be a raised to the power 6 raised to the power 4, and it can be written as a raised to the power 24. So 7, 7, 7 into a raised to the power 3. And you can check phi a raised to the power 7. So a raised to the power 7 raised to the power 4 it will be a raised to the power 28, and you can write a raised to the power 7, 7, 7 and 7. And this is E, 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 E. So all element of degree higher than 6 will repeat here. So you can check as you put input, you will get output for phi, output, and each output there exists a domain elements or input. For each output there exists a input, and these inputs are coming from G, group G. So phi is onto, and clearly for each input, there is distinct output. So phi is also 1 1, phi is 1 1. Now here we got 2 points about phi is 1 1 and onto. Now we have to check onto property. As G is cyclic and order of G is 7, because 7 is prime, and every prime order group is cyclic and every cyclic group is abelian. If two elements xy is coming from G, then xy will come to or will go to G by closure. If this is an element, apply phi, and by the property of phi, input raised to the power 4, and because G is abelian, so a b raised to the power n can be written as a raised to the power n b raised to the power n when a b are elements of G. So it can be written as x raised to the power 4, y raised to the power 4, and x raised to the power 4 means phi x into this is phi y. That is, phi of xy can be written as phi x, phi y. So phi is homomorphism, and these are arbitrary element. So all first three options discard. So correct options is D.